Thank you, and good morning, everybody. Hope you've all had your coffee this morning. Well, you all saw me yesterday, so I won't bother introducing myself again. So I'll just jump straight into this. That's the exciting part. It gets more boring from here on in. Okay, so this is not a general talk about performance optimization. This is not a general talk about all sorts of different tips and tricks you can use to tune your DPK application. This is a worked example, if you want, of one case where we were able to find performance optimizations using VTune analysis. Okay? In fact, the optimization found here and discussed here was largely found by accident. I was doing some investigation of RSS behavior in the driver. I don't remember the exact details of it, so don't bother asking me what I was actually looking for, but this is what I found instead, which turned out to be far more interesting. And the hope here is that the walkthrough of what the analysis I did would prove useful for other people when they're maybe trying to get better performance out of their applications. So, for those who don't know a bit about VTune, VTune is a tool produced by Intel for performance analysis and for debugging. It is a commercial tool, it's not freely available, though there is a free trial available for download if you go to the website. I see a free trial option there. So this is what I would use quite a lot whenever I'm trying to do some performance analysis. It's quite a powerful tool because it gives you access to the different hardware counters and can show you all sorts of details about, stalls in the CPU pipeline for L3 misses, branch miss predicts, lots and lots of information like that. So nearly too much information. It does take a while, I find, to get used to it. I'm by no means an expert on it, just the more I use it, the more familiar I get with it, the more that I tend to get out of it. So that's a bit of an introduction on the tool that I was using. Then the test setup I had was very, very simple. 2 ports using NICs that have been here to reference always as FortFill, but they're actually XL710s. I won't go using the F word or referring to them as FortFill either. Traffic generator, which was Ixia, I think, and just standard Xeon V3 CPU there, so that was Haswell microarchitecture. So packets in, packets out, bidirectional test. So there was nothing terribly complicated about this. I just got that, run traffic through it, and looked at the VTune results. And with my analysis, this is a snapshot of what the results were. Now, I don't expect you to read all the text and all these and see all the numbers. I do zoom in on some critical ones. But some of this was largely as expected. The first one highlighted is that the process was back-end bound. That's kind of what we expect. The actual execution of the CPU instructions was what was taking most of the time. We didn't have any instruction decoding issues. Some other numbers that stand out is that we got some delays, some slowdown reading L3. Well, the packet data from the NICs gets written to L3, so that's expected. However, there was this item here, which wasn't expected. Okay, we got a big red highlight around this item of loads blocked by store forwarding. And this is what turned out to be interesting. I was like, what is that? Why is it causing a slowdown in my program? And thankfully in VTune, if you put the mouse over, it'll give you a little bubble with a bit better description of what exactly the issue in question is. So for our driver, the issue was the store forwarding. And what does that mean? It's where we're doing a write to a memory location. Then, a few cycles later on, or a bit later on, we're actually doing a read from the same memory location, but the read is for a larger amount of data than what we wrote. Okay, so the read is then getting blocked by the write. If they were the same size, or the read was smaller than the amount of data we'd written, we could just do what's called store forwarding, and take the data from our buffers in the core and just pass it back as the read. If the write occurred well before the read, then the write would have flushed out to cache, to our L1 cache, or L2, L3, wherever it got evicted to, and we could pull it back in again as a regular read. However, in this case, the read was for more data, and it hadn't been fully flushed out. So the store forwarding couldn't work, and so we had to hold up the CPU, waiting for its data read until the write had completed. Okay, so we had a stall there because of that. And why this is unusual is it's not something that you generally expect to see in some good code. And it was not something that I ever expected to see cropping up inside any of our pull mode drivers, because I thought they were, they are pretty well written and they're pretty well optimized, so why was this showing up? So I decided to dig a little bit deeper. Okay? The nice thing about VTune is you can actually, using the magic of double click, you can actually go to the C code line in question where this is showing up, and then dig into the assembly code where this is showing up. Again, I've got zoom ins, don't worry, you don't have to try and read this. So this is just showing what the VTune window looks like. You've got your C code on the left, and your assembly code drilling down to the same line of C code on the right. So what showed up here? Okay, we had the actual instruction that VTune thought was causing this stall was the shuffle instruction, highlighted in bold there. Okay? Well, that corresponded to, in assembly, were the following instructions. It actually corresponded to two instructions, which is why there's two blue lines. It corresponded to move instruction and then the actual shuffle instruction. Okay? But it said that the stall was occurring on the move instruction. And that's fair enough, because this was a read that was stalling waiting for a write. So that move is a read. Okay. That's fair enough. We've pretty much found what we're looking for. The one note I'd add here is that in VTune, the line of assembly code that it says is causing the stall is not necessarily the one that could be causing it. It could be one further back, or maybe two or three further back, due to something called event-skate. If you run Google for it, you'll find a bit more details on that. But in this case, the actual instruction that highlighted and the previous instruction, they were both reads. They are both reads of NIC descriptors. So we can be pretty sure that this was probably the cause of our issue. They were also 16-byte reads, so they're pretty big reads. So again, this is where we got a bigger read than a smaller write. So we're pretty sure we found the actual real cause of the stall. So if we find the read, we need to find the actual culprit being the earlier write. Okay? So the nice thing about this driver code was that we had a compiler barrier put in right before those reads. So we don't need to worry about the compiler reordering, reads and writes around that. So we know it's just somewhere before that barrier. Okay, we don't need to look further down the code for something that the compiler might have pushed about the place. And the other thing we know is that the write must be smaller than 128 bits. Okay, well, most writes are in non-vector code, but in the vector code, we'd have to find one. Okay, but that wasn't all that was going on. The other thing that kind of confused me was the intrinsics for these SSE or AVX operations. Generally, but not always, they generally correspond to one assembly instruction. So the shuffle intrinsic is meant to just be the shuffle CPU instruction. But for some reason, why is it corresponding to two? A load and a shuffle. Especially since a couple of lines earlier in the code, we actually had put in a load intrinsic specifically to load that value before we did the shuffle on it. So, because I was confused with this, again, dig into VTune and have a look at what it says the assembly for that line of code is. So we look at our load for the descriptor, and then we look at the corresponding instructions. And we find, again, instead of one assembly instruction, we've got two, which happens to be a load and a store. So why would a load instruction be causing the compiler to emit a store instruction? So now we've got two mysteries that have to be solved. So, okay, in the absence of any other hints, I decided to look through the intermediate code, the code between our load and our shuffle, to see if that would give a hint as to why this strange event was occurring. Okay? The only work done on those descriptors between the load and the shuffle was in this function descriptor packet length align, to, as the name suggests, take the packet length value from the descriptor and line it up, because it was actually misaligned, it wasn't aligned on a byte boundary inside the descriptor. So, down to assembly, using VTune. Now, the actual instructions don't really matter, but what showed up was we had a nice block of vector code, and then that was followed by a block of scalar code that wasn't using vector instructions. I thought, this is a vector driver. We've got some scalar instructions in here. Yeah, let's look a bit more at those, because scalar instructions and scalar writes would be smaller than our vector reads, so that could be our potential source of the problem. And sure enough, it turned out to be right. There were writes in there that were causing the problem. So here it is in a little bit of detail, okay? Whenever we were taking the lengths of the packet, and actually writing them, filling them into the descriptor array, taking them from really the descriptors and then going to store them in the mbuff. Though in fact we're assigning to the descriptor variable here. That's essentially what we're doing, is taking them, moving them to the correct position and getting ready to write them to the mbuff. We were assigning the lengths using 16-bit writes because they were 16-bit values. But unfortunately, if you've got your descriptor in an XMM register, you can't just do a 16-bit assignment into the middle of an XMM register. The only way that can be done is by writing that XMM value out to memory, or to the stack, filling in the 16-bit value in the middle of it, and then reloading it again. So that's exactly what was happening here. What was happening was, whenever we did the load, the compiler then saw that, hang on, later on you're doing a 16-bit write in the middle of this, so I better write it to the stack for you. Then, after you've done your 16-bit write, I'll load it back up into the XMM register to do my shuffle. That's then what caused our problem. The read that we had was then stalling. So the fix for this was to get rid of those 16-bit stores. Rewrite it to do everything in vector instructions. Now, this was the first simple version of it that I did. It wasn't actually the final version I upstreamed because I found one that didn't rely on a series of instructions where each instruction depended on the previous one. But this was the first attempt to fix a problem and it worked quite well. The second one didn't really give any additional performance improvement, but it just seemed to be better code, not to have a sequence of instructions with one depending on each other. It doesn't give much scope for the CPU to try and run things in parallel. So, by using a series of blends and shifts, I was able to do the same work that we were doing in scalar code and vector. So this meant that we could keep all the data in the XMM registers, it could save the unnecessary loads and stores, which meant we got rid of the stalls and the store forwarding stalls on the load. That improved the performance and hey, makes everybody happy. And then to sanity check this, I did a subsequent VTune analysis run on it, exact same setup, exact same analysis, and the difference in the results was, in terms of the raw VTune, numbers for that store forwarding error were quite dramatic. It went from 0.18, nearly 0.19 to 0.01 and stopped being a hotspot in the code entirely. In terms of the actual PMD performance, this one change from removing that one bottleneck gave us over 5% here. I think the actual measured performance increase was about 8%, maybe even a little bit higher than that performance using test PMD of that driver, just by getting rid of that one bottleneck inside the code. So that's the worked example. Are there any questions on this?
I saw the order of code what you showed. I saw that read was first and the write was later. But I think the example what you're saying is the write coming first and then the read coming later is a problem. But I thought the code you showed, it was the other way.
No, what was happening was that what should have been a read was triggering a read and a write, because we were then having to do a subsequent write into the middle of that data, so we had to write it back out. And then whenever we went to do the shuffle, we had to do a second read. So we're actually reading the data twice. Once taking it from the descriptor ring in memory, putting it on the stack, and then later on pulling it from the stack, and then doing the actual vector manipulation on it to write it to the mbuff. Okay, and it was all caused by doing the 16-bit reads into the middle of that piece of data that otherwise would have been kept in registers. It had to be written out to memory.
So the other question I have is, you were talking about you're doing fencing anyway, right, between the write and read. So then already that is a stalling mechanism.
This was not a full fence, this was simply a compiler barrier to prevent the compiler reordering it. And it just made my life easier when trying to trace this, because I didn't have to worry about the compiler having moved inadvertently something I'd written sooner to be later, or vice versa. So that was all that was in there. So there's a couple of questions back here.
Bruce, so I think it's a very good topic, following with Thomas' introduction about how to get code in a generic way, because here we are in the PMD, and we have this PMD that only works fine on the Intel.
Yeah.
And since vectorized instructions about the same are available with Neon and Altirex, there are some equivalents, and they will have exactly the same pain, because there's about the same kind of behavior with the other CPUs. So I'm wondering if, for instance, here when you use VTune, if you could, instead of using the MM Intel IntuSync, if you could try to use some GCC built-in, we vectorize GCC, because the override, I mean, the GCC will generate exactly the same assembly instructions without overrides, most likely. So then the work you do will apply and will allow to reuse the same Intel NIC, but on ARM and Power CPU, not just on Intel.
Yeah. Yes, I mean, that's something that's been asked for before, and I agree it would be really great to have. However, if you look at the intrinsics we're using here, I don't believe there's GCC built-in intrinsics for things like shuffles and blends and things like that. However, I haven't looked into that much detail, but I think it's the more basic instructions. If those become more capable, by all means we should certainly look at using them to get that cross-instruction set portability. I mean, for us as well, I mean, this is SSE code. If we want to have AVX versions, AVX2 versions, AVX 512 versions, all these, you know, it's a pain for us, even in Intel, maintaining these different instruction sets ourselves. And we would like to have one generic set of GCC intrinsics that will just, we can compile up for a 128-bit vector, a 256-bit vector, or a 512-bit vector. So completely agree. Don't think we can do it just yet. But I'm quite happy to be proven wrong by that if somebody can come up with some proof of concept code to demonstrate it. But it's definitely something we'll keep in mind.
Yes, thank you, Chris.
My question is about the sampling method and the methodology here for discovering this bottleneck. So it looks like the top-down methodology described by in Intel manuals, isn't it?
Sorry, I didn't quite
Okay,
catch
so
it.
my question was about the methodology of discovering this bottleneck, because it looks like the top-down methodology, you know, used by Intel and their own performance counters, right?
Yeah, so this is using the hardware performance counters, yes.
Yeah, but the methodology of discovering the bottleneck is not just, there's no counter that shows you, you know, the bottleneck. It's the methodology to use the counters to calculate what is the bottleneck, right? And my question is it just gather like from a whole program, just like you measure for a couple of seconds, collect all the counters, and then it gives you a hint, or is it just a small fine-grained profiling of one function or something else?
It's hard in a lot of cases, in my experience anyway. Whenever I'm running this sort of thing, I try to limit it to just selected areas of interest. If I'm running a bigger application, I will generally just tell VTune, when it's getting its performance counters, to only pull them from the one core in question. I drill down into specific functions, specific areas. This case, it was one stat I was looking at, so I just let VTune show me the point in the code where it said the problem was, and then work backwards from there.
I see, so you saw a stall event somewhere that you think it shouldn't be?
Exactly, yes.
All right, because sometimes, you know, we've got perf, which is like a simplified version of this one.
Yeah.
And you can collect quite a lot of statistics, but if you do a perf stat over a running program, basically it might be just too much, you know,
yeah.
Like the program might be doing many things at once. For example, reception and transmission, and then your data is polluted. Okay, so
yeah.
So my question was about, does VTune actually do like fine-grained profiling of some smaller blocks of code, not just whole program?
The hardware counters are per core,
yeah.
But whenever you look at the results, it will give you the results per function. So if this was live VTune now and I clicked on that loads block per store forwarding, it would give me a list of all the functions in my code, and it would show the individual per function load blocked by store forwarding errors for each individual functions. So that's the way we generally do the analysis. In most cases, when I'm looking at things, it would be the L3 bound. Find out where exactly we're stalling on L3 reads. And VTune is very good about giving us a list of all the functions that have a high proportion of L3 misses. And then I find it simply a matter of just going into function by function, see, okay, this is where I've got L3 stalls in this function. Now, is there anything I can do about it? In many cases, unfortunately, there's not a lot I can do about it, but sometimes I can.
Okay, so so there was a one performance counter that was showing the event like this. The right after read hazard or the other way. So basically, so you tell that there was one hardware event that was triggered by this by this problem, and you could just zoom in and calculate one option. Okay.
So let me go back to the earlier screenshot. It was doing exactly that. So what you have being shown here, again, the interface is very fine detail with lots of small fonts, but you have the C code on the left, and in these columns here, the titles aren't actually shown because of the way I cut this, but across the top, it's actually got the names of all the stats in detail, showing for each line of code. This line of code had 0 branch mispredicts, 0 machine clears, but it had 2 L2 stalls, or, well, not 2, but 0.0 what percentage caused L2 stalls, L3 stalls for each line of code. And similarly, if you open the assembly window, it does the exact same thing with all the columns, with all these numbers that are there in light gray. They're the individual machine stats for that particular line of code. Okay? Though, as I said, the machine scape can make it a little fuzzy as to exactly which line of code it is. Some are more precise than others. And there are precise events and non-precise events, but I don't want to get into that. I'm not an expert on that specific detail of it. But that's how you can drill down per function, per line of code, and see the specific hardware stats, which can be very useful. But it's not a tool that's will always solve your problem, but it's one that's useful to have in your toolbox, I find.
So, Bruce, I have a question. Is there any ghost of a chance that we could have compiler support for the compiler doing the vectorization itself, rather than having to either use intrinsics or basically almost reverting to assembly logic to do this? Because compilers have a whole lot more knowledge of data flow and everything else than we can juggle in our head very easily.
Yeah, I have looked at the auto-vectorization of compilers in the past, but I will say that was a couple of years ago. I found it rather fiddly, and I actually found it harder in many ways than actually going in and using the intrinsics, because I knew what instruction I wanted to use in these cases, rather than trying to work out how to write it in such a way that would tell the compiler that I actually meant to use that instruction, which is what we wanted in these cases. Because we knew exactly what instruction in what case, in what order we wanted to use. I would say we'd have a better chance if we wanted fully generic code of getting GCC built-in intrinsics. Would probably be a better path for something like this. But I haven't looked at it in a couple of years.
Yeah, I can also share some of the things. So we use auto-vectorization a lot in experimental in a lab pack. And the point was, you could get cases where it works pretty well, even better than a manual thing, but since it was auto-vectorization, we quite often enough faced things where it's like, oh, we need a bug fix for whatever, you changed a mask by a byte, and the auto-vectorization no more hit. So when it fixed the issue, it suddenly changed totally what happened. So it's a good thing to have it enabled because it doesn't kill you, but for the real hot loops, it's too much of a risk to drop out of the auto feature, at least so far.
Okay, thank you very much, Bruce.